Thank you. Thank you. Hi, everyone. Thank you for joining in. Before I start, just want to give a quick shout out to Hackfest for having me here. This is my first Hackfest, and I'm absolutely loving it, but that might change depending on if you get my jokes or not. I also want to give a shout out to one of my ex-colleague, Nick, who also contributed to this research. His name and handle is down there. But yeah, he couldn't be here. Priorities. I am Saurabh Harit, goes by the handle 0xSabi. I work at Mandiant, and much like everyone else these days, I'm also a red teamer because it's been trending a lot. I also like to call myself a wannabe reverse engineer because I started my career as a reverse engineer, but I don't get to do that very often these days. This is what the agenda for the talk looks like. I have first 5 topics to kill time, and then I'll jump into case studies where I'll talk about different vulnerabilities that we discovered in 2 medical devices. In a typical InfoSec-style presentation, I won't be providing any solution to any of the problems I'll talk about today, but there will be some very generic remarks in the end. Just wanted to have a disclaimer at the beginning of the talk. The talk is not about bad-mouthing anyone, so I won't be naming any vendors or device names. Also, FDA was breathing down on my neck. Also, these devices are installed or deployed at different medical institutions. So with that, I apologize for heavily redacted screenshots that are coming up that might put NSA to shame. So a little bit about connected healthcare devices. They are well connected. They could be connected to a private network. They could be connected to internet. They can talk on different protocols like Wi-Fi, Lo-Fi, Zigbee, and so on. And they fall under the umbrella of IoT devices, which is the bigger umbrella. And there are tons of IoT devices out there, and which is becoming a problem because they're just coming out into the market, and there aren't much security features built into those devices. And also the fact that medical connected devices, I get why there's a need for those devices. But at the same time, there are other IoT devices that I just don't get behind. So things like your fridge connected to internet, your toaster connected to internet, or washing machine. So let's just think about this for a moment. Let's just assume that I have an internet-connected washing machine, right? So how it would go down is I'll take my dirty laundry, put it in the machine, and at that moment, I can make a decision to just press that big red blinking button right there. Or I can run to my basement, log onto my laptop, connect to the washing machine over Wi-Fi, and then start it. And because I'm an idiot, I'm now wondering, did it even work? So I'll run back upstairs to see if it works. So yeah, tough choice. So I've tried to classify medical devices into 5 different categories, and the first one is consumer wearables, which you would be most familiar with. So these are your fitness trackers, sleep pattern monitors, and so on. Then there are patient monitoring devices, which are your insulin pumps, blood pressure monitors. Then there are something called IVD, or in vitro medical devices, and your HIV detection systems, blood analyzers fall in that category. And so all the devices that I've talked about so far are external to a patient's body, hopefully. And then there are devices which are embedded into patient's body. So pacemaker would be the most common example of those devices. And then there are devices which you see at hospitals and medical institutions, which are bulky, stationary equipment, like medical dispensing system, MRI machines, CT scanner, X-ray machines. And some of these devices that fall under this in-house equipment category, they are also referred to as legacy devices, in the sense that they were never meant to be connected to a network, but because everyone is connecting everything, so why not these devices as well? And so I'll talk about in a bit how these devices are connected to a network and what kind of risk is then exposed from these devices. So this is what the data loop of a typical connected medical device looks like. So the device in itself is in constant monitoring mode using a sensor. And then in case it detects an event, it creates a trigger using the onboard chip, which takes an action, and then the data is aggregated and analyzed. And I think that the part where the data is aggregated and analyzed is going to be the key for connected medical devices, because that data can then be used by device manufacturers, medical practitioners to provide a better experience for the patient. So if you take example of a simple insulin pump, it constantly monitors the patient's insulin level, and if it sees there's a drop in patient's insulin level, then it uses the onboard chip to inject insulin in patient's body, which is done using the catheter that is usually placed under patient's skin. And then that data is aggregated and analyzed. So in terms of architecture, the medical device itself, which is on my side, has a lot of subsystems. As I mentioned, it can talk over a lot of different protocols. It would have sensors and actuators to detect a variation in pattern. It would have a display. It might have a location a tracker, like if it's a device that's monitoring your location, tracking your steps, and so on. Device association is the module that handles the authentication and authorization of a device to different connected systems. It would have a small storage to store data temporarily. Event architecture is the key module, which basically takes data and then creates an event based on that data. And then for some of the devices, well, actually, for most of the connected medical devices, there will be some sort of command and control module, which would allow manufacturers to remotely maintain the device and upgrade it and so on. Could also be used by the attacker sometimes. Then there's middleware, and you can think of middleware as the application server for your medical device, and that has most of the logic for authentication, authorization, remote access, and so on. But the most important part of middleware is going to be the storage, processing, and audit, the data storage part of it, because that module takes or aggregates data from all these different medical devices and then outputs consumable data, which then can be fed into like different kind of portals. So device manufacturers can access that data to see how the device is behaving in different scenarios and then better the device using that data. Can be used by security researchers across the globe, can be used by your doctors to take preventive measures based on your condition, and so on and so forth. So why do we need connected medical devices? And there are several reasons behind it. So first of all, it allows for remote health monitoring, so which means that if you have a connected medical device, you won't have to go for a doctor's visit that often, which cuts down on cost and time. And not just on the patient's part, because medical practitioners are almost always overstressed, it'll also cut down effort on their side. It'll also lead to less expenditure because you don't have to go to visit the doctor, which might incur a fee. There could be faster response time, so the devices itself may alert you for certain conditions. Doctors may take preventive measures based on your situation. Global healthcare is another big factor, and it's not happening that much right now, but think of the application of connected medical devices in underdeveloped countries where the medical staff is always a scarcity. Since all these medical devices are connected to a central system, it becomes very easy to maintain them and upgrade them if need be. Alerts, so for example, insulin pump is monitoring patient's insulin level, so if it sees a deviation from the normality, it can inform a patient, and then they can take preventive action based on that alert. And then the future of connected medical devices are going to be EHR and RTHS. And EHR are electronic health record systems, where all this data is aggregated and then saved for future analysis. But EHR were never meant to interact with medical devices in real time, so that they're limited in their capability as to what they can do. But RTHS, which is real-time health systems, are more able to take that kind of action and interact with different devices. So just a while back, I mentioned that some of the devices are considered legacy devices in the sense that they were never meant to be connected to the network, right? And so the way these devices are connected to a network are using serial to Ethernet converters. And serial to Ethernet converters using those devices are just generally a bad idea because there are tons of vulnerabilities in them. They talk over the serial communication port, which never had any security built into it. So the Department of Homeland Security in 2015, they issued an alert against one of the most commonly used serial to Ethernet converters, which is NPort, developed by a company called Merxa. And so there were a bunch of vulnerabilities that were discovered and reported in NPort. And one was that it would allow an attacker to extract sensitive information from these devices remotely and unauthenticated. The other one would allow an attacker to upgrade or downgrade a firmware on one of these devices, also remotely, also unauthenticated. And as if that was not enough, there was also a buffer overflow vulnerability that would allow an attacker to execute code remotely without any authentication. So generally a bad idea. And I don't know if you remember, there was a massive power outage in Ukraine in 2015. And as per DHS, that was also caused by attackers corrupting firmware on one of the serial to Ethernet converters. So in terms of the attack surface, like depending on the size of the medical device, so like insulin pump isn't that big a device, and so like if you look at them, they look like small trivial devices. But if you look at the attack surface, so like they have a lot of subsystems. So there's network part of it. Then there's application associated with the medical device. There's the physical device hardware itself. There could be a mobile application associated with the medical device. And then there's cloud infrastructure, which is supporting the particular medical device. So if you look at the attack surface, it's like actually quite large. And like vulnerabilities from different platforms could be exposed through a single small medical device. So there have been a lot of horror stories or incidents associated with connected medical devices. I just specifically wanted to talk about MedJack and MedJack 2 because they had the most impact. They were most noticeable among others. So MedJack, or medical device hijack, was a malware that came out in 2015, lived through 2016. MedJack 2 is basically a more evolved and sophisticated version of MedJack. It came out in 2017. And so one of the tricky things about MedJack was that it went almost undetected by endpoint security solutions. And the reason it happened was because MedJack was specifically targeting older operating systems and older vulnerabilities. So operating systems like Windows XP, 2000, 2K3, and we are talking about vulnerabilities like MS08067. And why it got undetected? Because the newer operating systems, they are protected against older vulnerabilities like MS08067. So they would just simply discard the malicious packet. So the packet won't even reach the endpoint security solution. And the older operating system which were running on these medical devices, they did not have an endpoint solution on the devices. So it was able to compromise tons of medical devices and then use the compromised devices to then pivot and compromise further systems. So I think it used Citadel and Zeus malware for horizontal movement and compromised other systems on the hospital network. All right, so I think I'm done with time filler slides and just going to jump onto case studies now. So the first medical device that we looked at was an IV infusion pump. And infusion pump is usually used to inject fluid, nutrients, medication into patient's body in a controlled and appropriate dosage. It's got some safety features built into it. So like medical practitioners can set soft and hard limits on an infusion pump. So for example, a doctor can come in and set morphine to be 100 milligrams as the maximum limit. And then once that is set, even if patient wanted to inject more morphine, they won't be able to. It used to be a standalone device, but now it's connected to the network. Also, this image is completely random. I am not capable of taking that good a picture. In terms of architecture, so this is what an infusion pump would look like in a hospital network. So it will connect to the hospital network either via Ethernet or wireless. It will talk to different subsystems on the hospital network. So pump server is something that infusion pump often talks to retrieve configurations and then save data onto. And then if the hospital decides to share the data collected from the infusion pump, they can do so by pushing the data out onto the cloud server, or then giving researchers access via VPN. So we've seen both kind of cases. Well, in our lab setup, we just had an infusion pump, so it wasn't connected to any network. We didn't have any pump server or any other components that usually talk to the infusion pump. So all we had was an infusion pump. In the lab, we made some initial observations. It had capability to connect over wireless, 802.11. It had proprietary power connectors. It also exposed an IRDA port. There was a display and a keypad. And there was a maintenance mode. So as soon as we found out about the maintenance mode, we frantically started Googling to see if there's some sort of manufacturer's guide out there which might expose the default password. And surely there was. And so we got the default password, and we tried that password on, and of course it worked, because you have no idea how much effort goes into changing the default passwords. It's just madness. Once we had the password, we were able to gain access to some of the network configurations, but it was only read-only access. So we could read some configurations, but we couldn't write any data onto it. There was an option to upgrade or downgrade the software, but I'm not that technical, and I have a life, so I didn't go that route. So we took the very obvious logical step, because we noticed that there was an IRDA port exposed. So from a pen tester's perspective, our next goal was to connect this infusion pump to our wireless network. Right? So we brought up our own access point, configured it with the same settings as on the infusion pump, but it didn't connect. And the reason it did not connect was because we did not it came pre-configured with a username and password, and we didn't know that username and password, and we couldn't change that username and password on the infusion pump. So we were kind of stuck. So we remember that there's an IRDA port that is exposed, so we took obvious next step. We went on eBay and bought a PDA. So the idea behind buying a PDA was to just buy a PDA and then get it to talk to the infusion pump over IRDA. And so we brought it back to our lab. We tried to make them connect to each other, and it just magically worked. There were no questions asked. PDA was like, hey, bro, do you want to talk? Infusion pump was like, yeah, sure, why not? We talk the same language, so let's just talk. So that worked out pretty well for us. And so once it was connected to the infusion pump, there was an option to export the network configurations through IRDA onto the PDA device, right? So we were really excited. We're like, yeah, this option is pretty cool, because we needed it to connect to a wireless network. So that's the route we tried. So what we did was, once we had the PDA connected to the infusion pump, we tried to export the wired configuration settings onto the PDA, and we were super pumped at this time, and we got it exported. And now we're opening this application on our PDA to bring up the template that was exported, and it was blank. So the template that we got on the PDA didn't have any relevant information. It had some information, but no sensitive information like username and password. So I guess someone from the manufacturer side figured that it's generally not a good idea to export sensitive information to a foreign device, which is good. So we were kind of stuck again, and at this point of time, we did what you typically do to a template. So we filled it. We filled it with our favorite wireless settings, and then ported it back to the infusion pump over IRDA. And out of everything else, that worked. So once we ported it back to the infusion pump, it just overwrote all its wireless settings from the settings from our template. So at this point of time, we configured it with the username and password. It got connected to our wireless access point. It was all good. So we made some more observations. So it exposed Telnet, FTP, and SSH. And we tried to brute force login for these services, but that didn't seem to work. I guess we need better word list for that. We also noticed that as soon as it got connected to the network, it started to look for a pump server. And from our previous knowledge, we knew that infusion pumps usually talk to pump servers. And so that confirmed what we already knew. But the problem was that we did not have a pump server in our lab. So we spun up a virtual machine, gave it the same net BIOS name as the new infusion pump was looking for, and just brought it up in the network. And as soon as that happened, the infusion pump started to send packets to the pump server. And we studied the packets for a while, and then it looked like it was loosely based on XML, and we were able to extract certain parameters. So if you look at the packet here, we could see the pump serial number, the current time, wireless access point data, IP MAC information, maintenance due date. And in the end, there was some random string, and which took us a while, but we figured that random string is actually X modem checksum. And because it's an X modem checksum, it was easy to spoof that. So we were able to retrieve packets, receive packets, modify them, and then push it back to the pump server after fixing the X modem checksum. So initially, we started doing it manually, but we figured that it might be a good idea at this point of time to start fuzzing this thing with different kind of packets. So we wrote a Python library, which would receive messages from the infusion pump, and then create different kind of responses, and then send it back to the infusion pump. And so after doing this for a while, we started deciphering some of the message types. So there was a message type 2, which confirmed to the pump that it is now connected to the pump server. So like if we receive a packet from infusion pump, we modify it, send a message type to, it'll confirm to the pump that it is now connected to the pump server. There was message type 7 and 31, which we're not really sure what they were. Message type 8 was usually followed by message type 2. And then once you send those messages, it changed the status on the infusion pump from listening to confirmed. Message type 20 was something to do with network commands. And then message type 208 and 238, we're not really sure. So we did a whole iteration of fuzzing, trying out different messages. And with one of the combinations, we were able to retrieve this packet. If you look here, there are different parameters which are quite sensitive information. So we're talking about there's a drug name parameter in there, dosage, care area, there's caregiver information, patient information, location, route, site. And you will see that all these fields here are empty, but that's just because our infusion pump didn't have real data. So in a real environment where it's deployed at a hospital, it will contain all that information. And once you receive that information, you can again update all that information and then fix the X modem checksum and then push it back to the infusion pump. And so we were able to do that. And one of the other things we were able to do through packet manipulation was gain access to something called master drug list. And remember how I talked about there was a case where doctors can set soft and hard limits on the dosage, right? So like 100 milligrams of morphine would be the upper limit. And so all that data is stored in the master drug list. And we weren't able to confirm this because we didn't have a real pump server in our lab environment. But there was strong indication that you can manipulate that data and then push it back to the infusion pump and then overwrite the master drug list. In that case, it should be pretty fatal. So these are some of the findings that we found in the infusion pump. The second device that we looked at, it was a digital pen, and the doctors would use it to write prescription electronically. So think of it as like a glorified fax machine, because doctors would write prescription with it. It will electronically be transferred to different pharmacies. And the idea is that by the time patient reaches the pharmacy, they would already have their prescription ready for pickup. So these pens are, again, manufactured by multiple manufacturers. We only looked at one device from one manufacturer. Also, this image is random as well. From the workflow perspective, that the pen or the device would connect to the hospital network using wired or wireless protocols, and then it will take the information which is written by the doctors, it will transmit it over SSL to the application server, which also expose data through a web portal. So like web portal would allow patients to view their own prescriptions. There would be a login for pharmacies to gain access to the prescription. There would be a login for manufacturers, and there would be a login for medical practitioners to look at that data. So we noticed that the pen came with Windows 10 operating system. It came pre-configured with two different accounts. One was the nurse/physician's account. The other one was an administrator account. And I suppose administrator one would be used by manufacturers to upgrade or downgrade the device. I think I'm the only other person who uses that account. It exposed USB. It could connect over Ethernet and Wi-Fi. It had HDMI and VGA interfaces, a digital display, audio ports. It came with fully updated Windows Defender. There was a docking station. So docking station had most of the functionality. So docking station is the one that had the USB port and VGA ports and all that. Then there was a software layer, which basically comprised of two applications that came from manufacturer. So since it had USB and HDMI and VGA, we could connect a keyboard, a mouse, and monitor to it. We noticed that once you boot up the pen, it automatically logs into nurse/physician account. So you don't need to provide a username and password. It's pre-configured to log in, but it would log in a lockdown mode, so you can't really do much with that mode. We noticed a couple of soft manufacturer applications and services running on the pen itself. While writing the prescription, if the pen is connected to the internet, it will transfer the data to the pharmacy in real time. But if it's not connected to the internet, then it will store that prescription in an encrypted manner on the disk of the pen. And then once you dock it and it connects to the internet, then it'll transfer data. The data was transmitted using SSL, so we looked at it, but there wasn't much in there. There was also a remote access component where it had TeamViewer installed, where manufacturers could log in remotely and connect to it to upgrade the device. So again, from pen tester's perspective, we were able to log in as a nurse physician in a lockdown mode, but the goal was to escalate privileges to local administrator, so we can do much more stuff. So we looked at different avenues. Like we tried different exploits that are out there for Windows 10 that didn't work. We looked at different services. We couldn't find any service which you could start, stop, or modify properties for. But we found one service, and ironically, it is one of the manufacturer's application, which it didn't allow us to restart the service, but it allowed us to change the service binary on the operating system. So again, typical pen tester stuff, we created a malicious payload that would just create a local admin when executed, and we replaced it with the actual binary for that particular service. And since we couldn't start or stop the service, we just rebooted the pen, and when it came back up, it created a local admin account. So at this point of time, we could do a lot more stuff in the sense that we could install a lot of tools on this particular pen. So we started off with some packet capturing tools like Wireshark, started looking at the traffic. But because it was using SSL, we didn't find much there to do. The other thing we did was we installed Procmon, which is part of System Internals utility. And if you've worked with Procmon before, you will see that it captures tons of events. Like surely you can filter it per application, but still there are a lot of events that are captured by Procmon. And so it basically monitors like file operations, memory operations, registry operations performed by an application. So we started monitoring that. And after a while, we observed that the application was trying to access the file with the extension ENC, which looked like an encrypted file. We located the file, we verified it, we opened it, it was all garbage strings, so definitely encrypted. So because I'm a wannabe reverse engineer, I thought this is my chance to start doing some reverse engineering. So I loaded up a system-level debugger on the operating system, started reverse engineering the logic of the particular application. So I was doing both static and dynamic reverse engineering. And basically, so on the left side, is the piece of assembly which is basically responsible for loading the file in memory and decrypting the content. So what I ended up doing was reversing the logic for decrypting the file, and just wrote a Python script that would just load the file and then decrypt the content of the file and save it onto another file. What I could have also done was just read the decrypted content from the buffer down there, but that didn't sound so fancy, so I just wrote my own Python script to do that. So, okay, so at this point of time, we were able to decrypt the content of the file, and so we noticed that it contains database connection string. So it contained like a username and password, it contained IP address of the MySQL database. I'm like, sure, okay, like this data is in there, it's probably redundant, there's no way they're using it. And even if they are, it's most likely, it's never going to happen that they will expose the MySQL database to the internet. But out of curiosity, I had to do a port scan, and surely the MySQL database was exposed to the internet. And so even at this point of time, I'm thinking this is one of those OSCP type CTF situations where like they want you to think that there's a vulnerability, but there isn't a vulnerability. Uh, but then we provide the username and password, it connected. And like I'm looking at my golden retriever, like because she's always watching me when I'm doing something interesting, and like, no way. And she's like, and so, yeah, so now we were able to connect to the backend database. And honestly, when I started looking at this device, I'm like, it looks like a small pen. In the best case scenario, I might just be able to capture some prescriptions that are stored on the device, but nothing more than that. But at this point of time, we were connected to the backend database as root, and we could access all the patient data from all the medical institutions these pens were deployed at, and not just our test pen. So if you look at some of the database content, so there's patient code, there's another patient code for some reason, then there's patient first name, last name, date of birth, gender of the patient, and so on. Tons of interesting tables. Like I couldn't include screenshots for all these tables, but here you can see that there's a column for username, password. Obviously, password was in plain text. And then there is something called a code. So the code tells you if that particular user is a patient, a manufacturer, an administrator, a doctor, or a pharmacist. So like you can take these logins and log onto the portal as like different users and gain access to even more medical records. So another thing we came across was you can see the resident name. So this is now from a particular health institution. So you can see resident name, the unit they're staying in, their home address, their room number, and HCN is basically their health card number, which is always obviously in plain text as well. And finally, we were also able to retrieve tons of prescriptions that were written by doctors for different patients, which we thought was not very cool. Right, so yeah, so this summarizes all the vulnerabilities that we found in these two medical devices. Just want to talk a bit about the challenges. And I think medical devices are going to grow, and they're going to go up in number. And one of the challenges for the medical institutions going forward would be that there will be tons of medical devices, and they need to make sure that they would have enough bandwidth to support all these medical devices. They would also need to make sure that there's enough segregation. Because there are going to be so many medical devices, how do you segregate the network? I was talking to a couple of people who work in the medical industry, are responsible for managing these networks, and one of them mentioned that how they do it is they put all the medical devices in one VLAN, and then the hospital systems in another VLAN, which is cool, but still doesn't solve the problem, because if one medical device gets compromised, then it can be used to compromise all other medical devices, right? And probably there will be a jump box somewhere which will allow you to jump onto the other system network. And then I suggested that perhaps we could, because in North America, in large hospitals, there are already around 12, 13 medical devices per bed. So I'm like, why can't we just do segregation per bed or per room? So that will, in that case, if the device is compromised, there's only going to be one poor bastard, but rest of the other people would be safe. But he's like, yeah, it'll be cool to do that, but that's not very functional. So like, it'll need a lot of budget, it'll need a lot of management. So I think in order to figure this out, there's going to need to be a better, more elaborate debate on how to best segregate the networks. Also, he mentioned that from their CISO's perspective, because they still have unpatched systems, older operating systems on their medical devices, the CISO's priority is to patch those systems. Their priority is to patch or get rid of Windows XP, Windows 2000, 2003, and not the medical devices. So we'll get to the medical devices, but it's going to take a long time to get there, which is an interesting conversation to have. Interoperability is going to be another issue because tons of devices, especially from different manufacturers, they talk on different protocols. So to get them to talk to each other is also going to be a challenge. Authentication and authorization could be a big challenge because I think we are approaching a time where, and I think it's still happening in some of the medical institutions where patients can bringing their own device in, which is connecting to the medical institution's network and then transferring data. So how do you differentiate between a legitimate device from a malicious device? And you can think of medical devices more like SCADA systems where functionality is priority over security. So they have to be online most of the time. So patching these devices isn't going to be an easy task to do. As a closing remark, these are pretty generic. I would say that because there's a lot of race in getting these devices out, the security is bolted on or rather than built into the devices. So the devices come out and then someone posts vulnerability disclosure for certain medical device and then they try to implement security on top of it, which has never actually worked. It's hard to trust devices, so it's hard to differentiate between legitimate medical devices and malicious or compromised medical devices. So that's another problem because network segmentation is going to be a problem. I think FDA has started to do a lot in terms of betterment of standards and regulations and the defining requirements for device manufacturers. But again, like we've seen time and again that getting compliant or just adhering to regulations isn't going to do it. So we need to go beyond that. And most importantly, like we've learned issues from other mistakes. So none of the issues actually I've talked about today are like exactly 0 days. They're pretty lame findings. And so we've seen those findings with web applications, mobile applications, other hardware. And we're making the same mistake again, where we think we're starting with a new product or new product line or domain and not learning from the past mistakes because the vulnerabilities are still going to be the same even in medical devices. And with that, I end my presentation. If you have any questions, please let me know.